Hello, everyone. Hello, everyone. Can you hear me? How's that? Hello. Hello. Am I on? Any better? Ah, there we go. Nothing like the sound of your own voice. Hello, everyone. Thank you for coming to my talk on virtual private cloud design. I know this is the last session of the day. I'd like to say that I'm going to take it easy on you, but I'm not. So I hope you save some brain cycles. We've got a really packed hour, so I'm going to get right into it. The first thing is a general disclaimer. Do try everything we discussed today at home. These are all proven use cases. Nothing I'm going to be describing is theoretical. These all come from customer cases that I work with on a day-to-day basis. I didn't introduce myself. My name is Rob Alexander. I'm an AWS Solutions Architect based out of Seattle, and I specialize in virtual private cloud. So my goal today is to empower you with what I consider good VPC design practices, to not only show you what is possible with VPC, but to show you how to do it well and what we consider in the best way. And through the talk, we're going to start with some very simple VPC designs. We're going to start with building up one VPC, and then we're going to move into much more complex use cases, and finally on to global VPC designs. So when my customers first think of VPC, usually their concerns and questions are focused on the isolation and the privacy that is obvious when we talk about what VPC is. But what's more interesting for me, coming specifically from a networking background, is back to what Andy highlighted today in the keynote, is agility. So he showed the little Karate Kid man on the tree stump. Agility is something that is traditionally not particularly associated with the networking side of the house in a lot of large enterprises. And it's something that I find personally most fun with VPC, is that you can design and deploy your networks at equal speed, whereas in the old world you would spend months and months and months racking and stacking and doing heavy lifting. So this ability to treat your physical network infrastructure programmatically, to be able to adjust and do designs on the fly, to be able to be creative and experiment with something that used to be a very physical thing and dependent on very physical resources. This is very particular to virtual private cloud. And it also allows you as a networking group to now adapt very quickly to changing business requirements, expansions, etc. So first, we're going to cover the general building blocks of what a VPC is, what it's made of, and how it works. I know most of you are probably familiar with a lot of the things we'll talk about in this first section, but it's important. I'm going to cover them, hopefully, from a viewpoint you haven't heard before. So we start with one VPC. A VPC is a private, isolated section of the AWS cloud where you define the networking within it. A VPC is across all the availability zones in a region, and there's only one thing you decide at the creation point, and that's what CIDR space, so what IP space to assign to your network. So our first VPC will be 10.1/16 with a 16-bit subnet mask. That's actually the largest CIDR block you can assign to a VPC. And we'll introduce our first subnets. Now, subnets, unlike the VPC, are availability zone specific. Subnets are where you define both your routing policy and your security policy at a subnet level. But we'll talk about that later. When you actually create the VPCs, the subnets, there's only three things that you designate. And that's the VPC to create them in, the AZ you want to create them in, and the CIDR block you want to assign to the subnet. So throughout the presentation, I'm going to have my little cloud dude here with the light bulb. And that's a general indicator of tips. So I just thrown in some various tips and tricks and things we've learned in the field as we've been working with VPC over the years. And so the first one is, a common headache with my customers is They start going into VPC and playing and creating networks, and pretty soon things stick and they start expanding more and more without thinking about their IP space in advance. And eventually they come to the point where they have conflicting IP spaces, and that's either with internal networks or that's with not holistically separating out your IP spaces across AZs. You know, maybe you only deploy in 2 AZs when you first start with your application, and later down the road you want to move on to 3, and you've not equally divided your subnet space across AZs for that region. And then when you move into other regions around the globe, you find, again, you need to consider unique IP space across the board for all of your AWS regions and VPCs. And the last point is key. Don't overlap your IP spaces, and we'll get to why that is a huge headache down the road. So back to our subnets, and the most common logical separation of the subnet purpose. So that's the public subnet and the private subnet. And the idea here is that resources that you deploy in a public subnet will eventually get public IPs and be able to egress out of the VPC. But at this point, these are just names. There's several more VPC components that need to be applied here before that can actually work. So at this point, it's just a name designation. So let's assign some CIDR blocks. For the public subnets, we've assigned a .1 and a .2, and for the private subnets, a .3 and a .4. All /24 subnet mask, just to make it nice and clean. So by default, every subnet in a VPC can talk to every other subnet. And that routing relationship is enabled by a virtual router that sits in a star topology between all the subnets. And now, to get to this router, the VPC DHCP service hands out a .1 default gateway for all the instances in that subnet. So what happens then? After it gets to the virtual router sitting between all the subnets, you actually have to have a routing table associated with the subnet itself. And by default, this is the single route that will exist in every single route table that you create. This local route is what actually defines the star and allows all the intra-subnet routing. So the second tip is leave the main route table alone. And what do I mean by main route table? Well, I mentioned earlier that when you create a subnet, you don't actually designate the routing table on creation point. You actually have to do that after you create the subnet. So every subnet by default has to have a routing policy applied, and so it inherits what we call the default or the main route table. So every subnet you create is going to have this table associated with it. So the tip is to leave it alone, because if you start messing with the main routing table, you could add a route to the outside world or a route to internal networks that you might not want applied to every subnet that's created in your VPC. So leave this one alone, and then create unique ones from then on to assign to your subnets. And you also note that it says it's associated with 0 subnets. That's actually not accurate. It's because it is the main routing table, and it's by default associated with any subnet that has not been explicitly associated with a subnet. So this local route that defines the virtual VPC router, it cannot be edited or deleted. And you also can't make a route that's more specific than it. So for example here, we're going to try to route to subnet 1 through an instance in subnet 2. And you obviously get an error. So this should give you a hint that routing tables in a VPC are actually not for defining any intra-VPC routing. They're specifically to define ways out of a VPC. But before we talk about the ways out, let's talk just a little bit about network security with a VPC. So that takes the form of both network ACLs and security groups. So you're probably familiar with security groups within AWS if you've done anything with EC2. But there's pretty significant differences in how the network ACLs work in conjunction to the security groups. So NACLs themselves are applied to subnets as a whole, so one per subnet. NACLs are stateless, so you actually have to define traffic coming both in and out, so they're quite rigid. And they're blacklists, so you can define rules for both allow and deny traffic. And last, they're processed in order that you create them, so it's very important as a best practice to make sure you put the most commonly matched rules at the top. You don't want to put /32 rules up top, very specific route, and work your way down. Security groups, on the other hand, are applied to instances themselves, and specifically, they're applied to elastic network interfaces on your instances. You can have up to 5 security groups per elastic network interface. Elastic security groups are stateful, so you don't have to define traffic in both directions. They're smart enough to maintain that connection for you, for the traffic going back out. And they're allow only, so you only define allow rules. And finally, they're evaluated as a whole, and a decision is made on the traffic on whether it's allowed or not. And within a VPC, the security groups can be used as destinations for your rules, source or destination. So you can actually use them as referential objects. So all of the instances that are contained in one security group can actually be a destination for one of your allow rules. This allows very easy referenceable layers in your application, and you're not worried about defining very specific IP blocks within your VPC for your allow rules. And we'll see that over and over again as we go through the use cases. So what are network ACLs really good for? So in general, they're good for enforcing very baseline policies. So for example, very specific traffic that you would never want to leave your internal network, it's a good catch-all for that. It's a good catch-all for misconfigured security groups. So if you have teams that are responsible for the network that are different from the teams that are responsible for applying security groups on your instances, there might be a mismatch there, and they apply the wrong security group, and therefore traffic could get out. These are a good catch-all. And like the last point says, it's a good segregation of duty. So you have folks that are in control of network security, and you have folks that are in charge of your application and instance security. So best practices with network ACLs. I always advise to use them quite sparingly. Some of my customers try to do quite a bit with network ACLs, and they end up creating more headaches than they're worth. I find security groups in general can do almost everything you need to do with NACLs, and they're much more flexible. So I like to advise to keep it simple. And it goes to the second point. You end up, when you start doing a lot of allow rules with NACLs, you end up having to define all these large ephemeral ports that have to go in the other direction to allow the traffic to flow. And different operating systems have different ranges, and you're worrying about keeping those consistent. So again, keep it simple. Create rule numbers with room to grow, so you leave nice big chunks between all your rules, so when you forget something, you can come back and very easily be able to insert them. And then finally, a very important point is use identity and access management to control very tightly who can go in and edit your network ACLs. And this goes in general good practice for IAM is to make sure that you have people that are responsible for the network are the only ones that can control and make changes on the network. And this is even more important if you don't use network ACLs, if you just go with the default network ACL that is applied to every subnet that you create, whether you know it or not, because it's listed there. It has an allow all rule, both in and out. And if someone goes in there and fat fingers that button, you've shut down your VPC completely. So it's something that exists in the background, and you have to make sure that these controls are in place. So here's an example of high blast radius VPC API calls that should be tightly restricted by IAM and given to a network operations group. And the 7 delete commands I've specifically highlighted because these support what we call EC2 resource permissions. So they allow you to very granularly dictate who can delete things. So for example, you could say this group of operations can only delete a customer gateway in this very specific VPC. So it allows a very fine level of detail in the policy. And here's an example of that. So in this IAM policy, I've tagged the actual NACLs with a tag that says prod. So any ACL that's labeled prod can only be executed by whatever group is applied with this policy. And for the extra paranoid, I've added at the bottom, you actually have to have an MFA authentication token to be able to execute this policy too. So if you log into the management console and you haven't used your MFA token to get a valid session, you wouldn't be able to run this command, even if you were a member of that group. So back to the ways out of a VPC. So there are two elements that can be added to a VPC that allow instances in the VPC to reach networks outside the VPC. The first is what I call the public door or the internet gateway, or IGW. So you attach an IGW in a one-to-one relationship to a VPC, and although I'm calling it a gateway, and a lot of these referential objects in VPC are called gateways, internet gateway, it's not a physical thing. So when you create an internet gateway and you attach it to a VPC, it's not a physical device that exists. It's a software configuration within the VPC networking stack that allows the potential for egress out of the VPC. It's not a bottleneck or something you have to worry about for bandwidth or availability. So there we have an IGW attached to our VPC now. And the second way out is the private door, or the virtual private gateway, VGW. And again, one VGW per one VPC. And VGWs are where you assign and logically attach both VPN tunnels and direct connect fiber connections. And like the IGW, the VGW is also a software configuration in the VPC networking stack. But unlike the IGW, at some point it actually breaks down to these VPN tunnels or these fiber connections, so you do have to be aware and manage for redundancy of those kind of connection options. So here we add a route table to subnet 4. We give a route for your internal CIDR block of your internal network, send it to the VGW, and out we go into your internal network. So back to public network access out the internet gateway. So even with the IGW attached to a VPC, we still need two more pieces before we can actually talk out. The first thing is a route table that points to the IGW that says, for this specific traffic, go out. So in this case, I've created kind of a default route that says anything that I don't know, send it to the IGW. It doesn't have to be everything. It can be very specific CIDR blocks that you want to be able to egress out for destination. But you need that, and you need a public IP. So in AWS, there's currently two ways to assign public IPs to instances in a VPC. The first one is one you're probably familiar with. It's been around for some time, that we call elastic IPs, or EIPs. And EIPs are good for any kind of traffic that you need to persist an IP for incoming traffic. So you ask for an EIP from us, we give you one, it's associated to your account, and it's yours from then on until you release it back to us. But it can persist across any instance. If an instance goes away, you can move it to another one. So it's very dynamic, but it stays the same. The opposite of this is automatic assignment of public IPs on launch. So as part of your EC2 launch command, you can flag to automatically assign this instance a public IP. And this is very similar to how EC2 Classic works. That public IP is dynamic. If you stop or start the instance, there's a good chance you'll lose that public IP. But it allows you to very easily, programmatically dish out public IPs to instances that don't have to persist for any incoming destination traffic. So here we see we've added a public IP to the instance. We've got the route table in place. And we can finally get out. But beyond getting to the internet, there are many services that live in public AWS that must be reached out of the VPC. So things like S3, DynamoDB, any public AWS endpoints. So think about anything inside your VPC, any instances that are calling CloudFormation or EC2 endpoints to change IP addresses, or SWF or SQS. Any regional services like S3 or DynamoDB, these are public endpoints in the public AWS space, and you have to get out of your VPC to get to them. Similarly, things like patch repositories, like for Amazon Linux, they also exist outside the VPC. So what if instance C needs to get out? It doesn't have a route table that's pointing to the IGW, doesn't have a public IP. And this is where the third option for getting out of a VPC comes into play, and that's what we call NAT, Network Address Translator. The idea is that you would deploy an instance as a NAT instance that would front the outgoing connection for any private instances in your VPC that wanted to get out. So it would have a public IP. That single public IP would front for any outgoing connections that you would need for private addresses that are going to keep private IPs only. So here's an example of what the route table would look like. So for that subnet, that private subnet, it says for any traffic you don't know about, send it to the NAT instance. So the NAT instance takes it. The NAT instance is obviously in a subnet that has a route table that points to the IGW, and it can get out. So we provide a default NAT AMI as part of our VPC creation tool, but there's nothing particularly special about the NAT itself. There's many marketplace vendors that provide equivalent security appliances, whether it's Cisco or Sophos or Brocade. So I wanted to point out here that what we actually do is quite simple, and these are just the commands that we actually run to turn something in a NAT interface. It's something that you could do in a Windows box or any other instance that you might be running. So other private subnets could share this same routing table and be able to use the NAT to get out. But obviously that NAT is a single EC2 instance at this point. So as we add more and more traffic, it's going to become a bandwidth bottleneck at some point. You know, it's one single instance. It only has a certain amount of bandwidth allocation. If it's funneling traffic for dozens and dozens of other instances behind it, eventually it's going to melt. So what are your options for making a scalable and available NAT solution? Before directly answering that question, I'm going to actually ask a question back. Because this automatic public IP assignment feature that I discussed is actually relatively new. It was only released back in, I think, October of last year. And before that, it was very hard to negotiate public IP assignments. But now, to be able to automatically dish them out, it's much simpler. So the first question you should ask yourself is, do these bandwidth-intensive processes really need to be behind a NAT? Do I need to be funneling all this traffic through a single instance? So separate out those application components that do need this high throughput out, and give them their own public IPs, allow them to talk full instance bandwidth out of the VPC. So the most common use case for this is, of course, access to S3. So many customers that are trying to push multi-gigabit streams of traffic through a NAT instance to get to S3. And it just doesn't scale through a single instance. So here's a design example. This is from a real customer use case of mine about what they did to handle the NAT bandwidth. So this is an image processing app that had high outbound requirements to S3. It would have customers that would come in, upload photos. There'd be some work done on those photos, metadata added, and many, many iterations of that photo, different resolutions, and those were all put back up into S3. So here we deploy a public elastic load balancer that would receive all those incoming customer requests. That's obviously in its own autoscaling group across 2 AZs. And the autoscaling group for the web servers itself is configured to automatically assign public IPs. So as the traffic grows and shrinks and this layer adds instances and takes away instances, anything that it adds is going to get public IPs automatically assigned to it. So customers come in, the traffic goes through the ELB and is distributed to the various web servers. The web servers do their job and then are able to upload straight up to S3, back out of the VPC and not go through the NAT. Now we still have the NAT there for any private application resources you have behind that might need, access to patch repositories or one-off accesses out, but it's not a bandwidth limiter anymore for your prime customer-facing infrastructure. And this is just the example of the autoscaling group launch configuration itself, and it's just that simple to make sure that any instance launched by this autoscaling group is given a public IP address. So the NAT's still there, and you still need to account for its availability. So how do you do that? What's best practice for that? So for this design, what we do is we create a NAT for each AZ, so that everything in that AZ is configured to point to that NAT instance. And therefore, it's almost like columns. Each AZ is a column, so any private subnets behind that NAT in that AZ are all pointing to the one NAT. And then we create what we call an availability autoscaling group on the NAT instance itself. And what this does is you set basically a one-to-one min-max on the autoscaling group, and therefore, if anything happens to that NAT, it falls over, it becomes unresponsive. Autoscaling itself handles the regeneration of that NAT for you. And the trick is to make sure that when that new NAT comes up, that it automatically configures the appropriate subnets to point to itself. Because if that NAT goes away, as you saw in the routing tables, you point to an actual instance as the NAT in the route. So if that instant fails and goes away, the next one that comes out is going to be a different instance ID, and that route in those existing route tables is now going to be invalid. So the trick is to programmatically and automatically adjust all your route tables to point to this new instance that's coming up. So this is just an example of what the autoscaling availability group would look like. Min-max of 1 and deployed only in one subnet. And this is a little script I wrote that does exactly what I was talking about. So this kind of gives you an example of some of the fun you can have with programmatic networks. So this is something you just copy and paste, and you dump in your user data for your autoscaling group. It's run every time any new instance comes up in the group. And basically, it does exactly that. It asks, who am I, where am I, and what am I supposed to be doing? And what I'm supposed to be doing is finding any subnet in my AZ that's labeled private, get the associated routing table for that subnet, and update it to point it to me. So this is a very simple and lightweight way to make sure you always have NAT availability in each AZ. And it also shows some of the fun you can have with the new AWS CLI. So you'll notice in there, there's things like query variables and filters. So the new AWS CLI, it's been around for 4 or 5 months, and this version allows you to, those of you that are much more comfortable with Bash than JSON, for example, there's some really cool tools in here that allow you to output text instead of JSON, which is notoriously hard to parse for a Bash guy. So that brings me to my next point, is to tag early, tag often, and tag everything. This was just a simple example of what you can do with tags, but like the IP space design I mentioned in the beginning, tagging should be something you're thinking of from the beginning and have a tagging strategy and schema for all of your AWS resources. It will save you great headaches in the future, and it will also provide some great flexibility. So whether it's your project code, your cost centers, environments, versions, teams, whatever makes sense to you, whatever answers questions for you and your business, use the tags to convey that. And make sure you enforce tag creation, or tagging upon creation, so that you're consistent. And audit that stuff. So you can have automatic processes that go out and describe all of your resources and gather tags and make sure you're enforcing that folks are putting the appropriate tags on the resources that they create. And obviously, billing also supports tagging, so it's very easy to break out how much this application costs you if you're tagging appropriately. And finally, if you're using tagging to control operational things, which you should, and you're tagging things as, for example, production, you need to make sure that you're tightly controlling who can actually tag things production and untag things production. So here's an example of the IAM policy that needs to go with the HA-NAT instance to make sure it can do everything it needs to do. When that HA-NAT instance comes up, it needs to be able to modify some attributes of itself. It needs to be able to describe subnets to get the subnet names and the route tables, and then finally to make changes to route tables. So this is an example of an EC2 role for that function. And the latest version of the script is available here. So for those of you who want to pull it down and play with it and see what you think, let me know. And finally, if your design requirements still maintain that you have to have a NAT and enforce that a certain amount of traffic is going through that NAT, your options are basically vertical scaling. So you use the one HA NAT design, vertically scale that NAT as your requirements start to increase, and keep a close watch on your CloudWatch network metrics. If you just hold your questions to the end, I'm sorry I didn't mention that in the beginning, but I'll stay as long as you want when we're done and answer all of your questions. But I just want to make sure we get through everything for everyone. Thank you. I wanted to mention something that Andy mentioned in the keynote this morning, is the enhanced networking feature that is a product of some of our newest instance types. So, for example, the C3s, the I2s, and the just announced today, the R3 instance types. Only in a VPC are they able to take advantage of enhanced networking features. So that's a much higher packet per second rate, lower jitter, lower network latency. So a great add-on feature that's only available in VPC, deploying these instances in the VPC. If you deploy an Amazon Linux HVM AMI, it's all set up for you by default. You'll get it out of the box. If you run other flavors of Linux or even Windows, it's absolutely configurable. It's just on your behalf, you have to install a driver and do some configuration for yourself. All the details there at that link. So moving on from the one VPC that we've now created that has a public-facing internet application, we start considering more VPCs in the same region. So I wanted to spend just a minute on what happens and what common customer use cases there are to consider moving to a multi-VPC model. So here you see the next consideration we have is that we want to move an internal company app up into the region. We want this to be a private only, and it's very distinct from the public-facing web app VPC that we've already built. So that seems to make sense. But what other common use cases are there? So here's the ones that we find the most. So there's really no hard and fast rules. The tools are built to be flexible so that you can decide what makes sense for your business. But in general, these are the most common ones. So the application isolation is what I've already discussed. So applications that are public-facing versus private, very easily to justify why you would separate those out into separate VPCs. Scope of audit containment is something more when you absolutely have to guarantee that all of these resources can only be touched by very specific people. And that usually can only be done as a hard separation with separate AWS accounts. And at that point, when you're different accounts, you're obviously different VPCs. And that's similar with a risk level separation. So if you have applications that have PCI compliance or high confidentiality requirements, again, those are good candidates for separating out into their own VPCs. And then separate production, non-production, that's an easy one. Lots of customers that are running multi-tenant apps, so they give a VPC per customer. And finally, I've got large enterprise customers that have a unique network design specific for their business units that they want to reflect in the cloud. So they bring their own structure where different VPCs represent different business units, for example. So our next use case, we're going to talk about this internal web application that we want to move up into the region, but that we want to keep completely private. We want to control the egress of that VPC. So we'd like to keep it where we actually wouldn't have to put an IGW on here and have the possibility of any traffic going out of the VPC. So how would you do that? So one of the options is to deploy a proxy layer. So here we see setup we've already had, but we're trying to avoid having an IGW, but the application itself needs access to S3. This is very common. Obviously, S3 is a great resource for storage, and lots of resources in a VPC need to talk to the S3. In a situation where the only connection is private, to get to S3 would be a very long and convoluted path, right? So you have to go all the way to your corporate data center, back out your own border network, out to the internet, and back into the region. Obviously not exactly ideal. So a proxy layer to sit between your corporate application and the actual egress out of the VPC. So how would you do this? You would restrict all outbound access to only URLs that you define. So in this case, we're talking about S3. None of your private subnets would actually have a route out. You would be configuring proxy variables on your instances themselves to use your proxy layer that you're setting up. So only the proxy layer itself would know about the way out, and then tightly control what can actually talk to the proxy layer, obviously. So this is what this might look like. So this time we're going to deploy an internal load balancer. So this is fronting the proxy layer to make sure it's highly available and scalable. We're going to add, in the private subnet, any instances that want to be able to talk to this load balancer. We're going to add them to a proxy security group. And so then configure the elastic load balancer. The only thing that can talk to that internal ELB is this security group. You're tightly controlling who can actually use the proxy. And that brings up a good point in general for deploying elastic load balancers in virtual private clouds, is that most people might not realize that we're actually taking EC2 instances and we're taking IPs in your subnets. When you deploy ELB in a VPC, the underlying infrastructure is actually EC2. And it's taking IPs out of your private IP space. So if there are particular IPs that you might be reserving in certain ranges in each subnet, you might find one day you come to claim that IP in a subnet, and it's not there because ELB has it. So I always recommend to make sure and keep ELB in its own layer. And that way you know where it is, you know what it does. And specifically, you can control the routing policy. So you have distinct routing tables for your ELB layer versus your application layer, and you're not mixing the same in the same subnets. So what would the rest of the infrastructure look like? Here's the public subnet. In this case, I've chosen Squid as my proxy layer. Again, we have many options here for a proxy, but for this one, we've stuck with Squid. Only the proxy subnets themselves have the route to the IGW. Obviously, the squids themselves are in a multi-AZ autoscaling group that's assigned to the Elastic Load Balancer. So any instance that has their proxy variable properly configured to point to the actual DNS name of the ELB can talk to the proxy, distributes out to all the proxy instances. They check the actual destination URL for where you're trying to go, and if it's the specific S3 bucket that you're allowing, out you go. So here's just a quick and easy example of how you'd set Squid up to do this. So this is just using Squid ACLs, so it's a combination of both IP address. So it's saying the IP addresses that are assigned to the proxy subnets combined with the destination domain URL, an AND of both of those things. If they're equal, then let the traffic pass. If not, deny everything else. And we actually have all the CloudFormation templates and everything you need to try this at home at this link. This is also a good option if your outbound traffic is all HTTP based. This is another option for scaling outbound NAT, so you could put proxies there, but obviously you'd be limited in the kind of traffic that you could use. So back to where we were with our VPC evolution. So in the region, we have now the two VPCs, the internal company app and the public-facing web app. The internal app is obviously connected to your data center back home. But it turns out that this internal app is quite popular. So everyone wants one. And soon you find yourself creating more and more VPN tunnels, more and more customer gateways. Each customer gateway must maintain its own public IP address. We actually, within each region, we present only 2 public IP addresses for the destinations of our VPN tunnels for all customers. So that means that it's on your end to keep the uniqueness of the IP address. So for every one of these customer gateways you're creating to terminate these VPN tunnels on your end, you're having to use another public IP address. And of course, we've all done this before, and we know as soon as we give this flexibility to a few groups, there's going to be more. And we know where this is going. So you're going to have development-focused ones, QA-focused ones, production-focused ones, and many of iterations of thereof. And pretty soon, you're going to be in the VPN business and not the running application infrastructure business, which is not a good place to be. Because now you're pushing back and forth a whole bunch of data, and you're accessing a whole bunch of shared services in your data centers. You're sending backups. You're doing database transfers from prod to QA. You're doing code releases. So all this traffic going up and down these VPN tunnels. So what are your options there? So this is, up until now, your best design option was something like this. So collapse everything in, run your own VPN infrastructure, have EC2 instances as VPN endpoints, and oh, guess what? You got to manage high availability for that, so you've got to have 2 EC2 instances as VPN endpoints in each VPC, and this really doesn't help the complexity problem that we spoke of earlier. It just kind of turns it inward and saves you the bandwidth problem. So I say enough with this headache. I had to have at least one Monty Python reference, sorry. So I woke up this morning. I don't know if anybody else checked. Yeah, thank you. As Andy said in his keynote, with AWS, upgrades happen automatically. Every day we go to sleep, and every morning we wake up, and there's new stuff. And last year we had new stuff. Every workday we had something new. So with the amount of features and releases we're doing, you never know what you're going to get. So this morning I woke up and VPC peering was alive. And so this is a feature that's been long requested by our customers. So I'm very happy to say that it's now here. And I'd like to show you how it works. So VPC peering is to address that problem we just saw. So within a region, how do you manage communication between your various VPCs easily and without having to run your own VPN infrastructure? So in this initial release of VPC peering, the VPCs themselves need to be in the same region. They can be same or different accounts, doesn't matter. And the peering itself works in kind of a will you be my friend basis. So you send a request to another VPC saying, here's a peer request, will you peer with me? And the other side has to answer back and say, yes, I'll peer with you. So you have this mutual agreement, and once that's agreed on both sides, then the peering connection itself is active. Now, that doesn't mean automatically traffic starts flowing. It just means that that connection itself is active. We'll get to how you actually make things flow. So back in the beginning when I mentioned about IP space overlap, that's the key requirement of peering, is that IP spaces can overlap. It won't allow you to do it. It won't allow the connection to go active if any part of your IP space is overlapping. And the last point is also important. So you can only have one peering relationship between any two VPCs. So as you see here, we bring in another VPC, which has the identical IP space of that VPC, and we try to create a peering connection, and that obviously fails. But interestingly, we can do that. So one VPC can be peered to two VPCs that have the same space. And we'll show how that works here in a minute. So we'll back up and we'll show how the actual routing happens once the connection itself is live. So here we are with a routing table. And you can now add routes that say, as your destination, peering connection. So it's very simple. So you say, to get to the CIDR block of VPC A, use this peering connection. And on the other side, you do the same. To get to the CIDR block of VPC B, use the same peering connection. So it's important to point out that there's no gateways required here, so that you don't have to have an IGW on these VPCs. You don't have to have a VGW. And there's also, there's no single point of failure. So similarly how I described the internet gateway, this is purely a software configuration of the VPC stack. So we're not introducing any physical presence. There's no physical thing that all this is flowing. This is purely an allowance for these two to now communicate. So there's not, you don't have to worry about VPN tunnels going down or anything like that. And by default, by that description, there's also no bandwidth bottlenecks by enabling peering. So instances themselves will still be, their bandwidth limitation will be determined by the instance type itself that you've chosen. So now back to the two VPCs with same space to the same, peered to the same VPC. So how would that work? And again, it's all driven by the routing tables. So you have two separate subnets in this one VPC, and you create separate routing tables for them. So for the subnet 1 on the left, we've got a destination for the same CIDR block for VPC B using the peering connection 1. For the second subnet, same CIDR block, but just a different peering connection. So you can get a very fine level of control at each subnet to what they're peered with. And you'll notice in these peering routes I've used so far, I've been designating the entire CIDR block of the peered VPC. That's actually not required either. You can get very specific. So here we've got an instance deployed in subnet 3 in VPC B, and we create a routing table that looks like this. So in this one, we're only giving him permission to see through the peering connection one very specific subnet. And on the reverse end, we've updated the route for subnet 1 in VPC A to be a /32, so it's only a very specific host that is able to use this peering connection. So you can get as specific as you want. Obviously, the most specific subnet mask wins. So a few more rules of the road when it comes to peering. If you remember your transitive math from grade school, A equals B, and B equals C, and therefore A equals C. Well, forget it. It doesn't work here either. So here we've got A paired with B, and A paired with C. This does not mean that C can talk to B. There are no inherent transitive relationships with VPC peering. Because I'm peered with another VPC does not mean that I get to see all the other peers that that VPC already has established. And this is great for isolation, as we'll see in our models. But it is something you need to keep in mind. If you wanted that peering relationship to happen, you would just establish a peering between B and C. So this means this rule also extends to things like VGWs and IGWs. So here we've got a VGW attached to the VPC with a connection back to your home data center. Does not mean this VPC can leverage that VGW connection to get back home. And similarly with an IGW, same deal. Peered VPC would not be able to leverage that IGW. Now, some of you may be raising an eyebrow on this one from a pure routing perspective. VPC peering by default does not allow you to do this. You certainly can do this with your own instances. I mean, if you've provided a proxy layer or a filtering layer that this traffic would land in that peered VPC and then move on, you could certainly get it to work. But just the peering relationship itself and these connections are not facilitating routing between the peers. So this, again, perfectly acceptable. And if you are so inclined, you can go full mesh. And it looks really busy, right? But it's not, really. It's only 6 or 7 peering connections per VPC. This is something that would be a massive headache if you were running your own VPN infrastructure. But with peering, it's not. 6 or 7 is nothing. The soft limit per VPC is 50 peering connections. There's a hard limit, I think we've set it at 125. But 50 is your soft, so it's a pretty good number. It's a pretty good degree of mesh complexity. It's very easy to roll out and obviously programmatic. So you start to see designs and patterns that in the old world of connecting things with VPN infrastructure just weren't possible. So to emphasize that flexibility, this is a fun one I've been working on with one of my customers. They have a multi-tenant application. So each customer is given their own account and their own VPC. And then they have a master control account, basically, that maintains an EC2 role in each of the other customer accounts so that they can do things operationally related in their customers' VPCs. But they literally have hundreds and hundreds and hundreds of VPCs, and so they didn't want to maintain anything like a full mesh. Their customers are standalone and isolated in what they do in their VPCs, but they had regulatory requirements to be able to do regular patch scans to make sure all the patches are updated, to do vulnerability scans, to do configuration audits. So we thought about in this new VPC, this new peering world, what kind of things could we play with? So I came up with this one. I call it the Night's Watch. So we create the Night's Watch VPC, which is a security operations VPC that contains all the infrastructure you need to do your security operations, your scanning machines, your auditing machines, your log collectors, etc. And it basically floats programmatically and automatically, going around connecting itself to your various VPCs, right? Connects to this one, does its job, does what it needs to, kills the connection, moves on to the next one, does its connection, does its scan, gathers the data it needs, kills it, moves on. So this is nothing you could ever have done in a physical networking world, running around moving cables. But it's just giving you an idea of some of the options that are now out there that you could start considering when it comes to peering. All right, stop that. So back to our actual design. So whereas before, it's still a very similar design, but you don't have any VPNs in this case. So we now have all these peering relationships set up. Each internal company app is a one-to-one peer to what we're calling a services VPC. So you've moved up all of these core shared services into a centralized VPC. Things like Active Directory, your naming service, monitoring, logging, whatever you need that are shared amongst all of your other customer VPCs. And then you create one-to-one peering relationships with the actual company apps. And the good part about this is that they're all now completely isolated from each other. You know, before, when you're running VPN tunnels, from a networking perspective, they actually could technically all talk to each other unless you're also running some fairly complex, you know, security and firewalls between them all. But here, by default, the peering relationship is one-to-one. So again, there's no transitive inheritance for any of these internal company apps to talk to another internal company app, just because they have a peer with the shared services. And it doesn't mean you couldn't do some ad hoc things. So, you know, this is very common where you would want to take down a copy of production data maybe and transfer it down to QA, you know, filtered, of course, for sensitive data, and put into your QA VPC to run some tests on. You could create a temporary peering connection, transfer your data, tear it down, and off you go. It's important to point out that security groups and NACLs absolutely still exist in a peering world. There's nothing different. They're still there. The one thing to point out is that security groups are still bound to the VPC that they were created in. So unlike within a VPC where you can reference other security groups, across peers you cannot. So the security group IDs themselves are only contained in the VPC, and you'll have to use CIDR blocks when you're talking about screening traffic from peered groups. So real quick, tip 8. This is using the new EC2 run resource permissions to control exactly what goes into your VPCs. So in our previous example, you know, we have shared services VPCs and customer VPCs. You want to make sure you can control who can do what in each one. And a key way to do that is the new functionality of EC2 Run to support resource permissions that allows you to have a very fine level of granularity of control of who can do what. So you can have things like this dev group can only launch these dev AMIs in this dev VPC. And if they try to launch an instance that doesn't have all of those requirements in the EC2 Run command, then the command will fail. And similarly with something like production, you might have very standardized and approved AMIs for your production deployments, and you can finally control not only who can deploy those AMIs, but what security groups can be on them and in which VPCs they can actually be launched in. There's more details in the link there. So, now here's what we look like. And unfortunately, we continue to grow, or more fortunately, actually. Now we've got replicated environments, and now we're getting back to where, again, dealing with VPN tunnels, and many of them, and pushing, maybe at this point, you might be pushing multi-gigabit per second traffic, and that's some pretty top-end VPN gear to handle that. And again, you're getting in the business of maintaining a lot of VPN tunnels as you grow and grow, and all these still need connectivity down into your data center. So what are your options there? So this section is all about bringing everything back home and leveraging your internal network when your VPCs grow to many regions. So a key simplifier for this architecture is the use of Direct Connect. So AWS Direct Connect is our private fiber service where you actually directly plug into an AWS region. So instead of running VPN connections over the public internet, you're actually using physical connections to us. And they come in many flavors, 50 to 500 megabit per second, and 1 gigabit or 10 gigabit pipes, or combinations thereof. And how it works is in a region, there will be a certain number of direct connects, at least one, associated with that region. And we run private fiber up to these locations. Now, these locations are usually large colo facilities like a Equinix or a core site where many customers are already highly concentrated. We'll set up a point of presence there and present, you know, a patch panel in a meet me room. And if you're already in that facility, it's a very easy process for you to just get a cross connect directly into us. If you're not already in that facility, then we have a whole bunch of partners that work with you to do that last mile, or you might even have your own pre-existing telco arrangements or working with a certain telco provider to get you there. But anything can get you there. So whether it's MPLS or Metro Ethernet or whatever it is to get you in that facility, then it's just a simple cross-connect into us. So a few more bits on Direct Connect. You can create private or public interfaces on the physical Direct Connect pipe. So you create these logical interfaces. The private ones are associated in a one-to-one relationship to a VPC. So obviously it has much more consistent network performance and guaranteed bandwidth. And we obviously always recommend you have redundant connections. And you can share these physical Direct Connects across multiple AWS accounts. So here's what it looks like when you actually run a bunch of VPCs over a single physical Direct Connect. Here we have VPC1 with the VGW. We create a private virtual interface on our Direct Connect connection with a distinct and unique VLAN tag. The BGP ASN there, that's 7224, that's AWS's. That's what we'll always give you. And out of that VPC will be advertised via BGP, the CIDR block for that VPC. The interface IP there I'm just using link local addresses. You can certainly assign whatever private IPs you want there. And on your side, you're going to create an interface that has the exact same VLAN tag. That's actually how we enforce the layer 2 pipe on both ends. It's just a unique VLAN tag per connection. Your ASN can be your own public BGP ASN if you want to use it, but it's perfectly fine to use private ones. This is just a one-to-one peer connection for BGP. And you announce, obviously, whatever you want to announce. And so you can go along connecting all your VPCs one-to-one, each creating a unique interface for that VPC in a one-to-one relationship. So here we just create another unique VLAN tag. And off we go. So now we have all the VPCs directly connected through Direct Connect back to our core data center. And the routing table itself is going to look something like this. So you're just, for those destinations that exist in the CIDR blocks in those VPCs, you're going to point to the interface on your end, or the private virtual interface on our side. And we don't actually route between the interfaces on our side. So for example, if VPC1 wants to talk to VPC3, that doesn't occur on our end. All the traffic comes down to you. You apply whatever routing policy you have to determine where that traffic goes. So that looks something like this. Comes down to you. Obviously, you direct it out back to where its destination is. Now, something new with Direct Connect in the United States is that once you connect in one location, you get access to all locations. So it's kind of a 1-for-4, free-for-all. So this applies to any AWS region, so US West 1, US West 2, US East 1, and even GovCloud. So what would that look like? For example, if you were based here in San Francisco and you had a presence and connectivity to the Direct Connect we have down in San Jose in the Equinix, you'd have a direct connection. The only one you would have is to US West 1. Now that would give you access to all your VPCs in that region via private virtual interfaces. And it would also give you public access to all the public resources in that region. But in the US, once you establish a public interface over Direct Connect into a region, you get access to all regions' public resources. So for example, if you're running S3 buckets out of Oregon in US West 2, that traffic would now go directly over your Direct Connect and over our private network between all of our regions to reach that bucket. And similarly, if you were running, say, a disaster recovery VPC on the East Coast that had its own VGW, that VGW obviously is associated to our public endpoints for VPN, so it's a publicly available resource. You could now access those VPCs directly. Unfortunately, you're doing a VPN at that point, though. So you can't completely get away from VPNs yet. But it's entirely possible now within the US to have one Direct Connect in and reach all of your resources in the other regions. So this is how that's done. You create, instead of a private interface on your Direct Connect, you're now creating a public interface. And what happens is the BGP announcement over that public interface is all the CIDR blocks for all of our regions in the US. So before this feature was released, you were only getting the CIDR blocks for that region you were connected to. Now you get all regions. So on your end, you obviously decide what it is you want to do with all of those regions. And your routing table will start to look something like this. Now, it's important to note that this is a public network, so you have to treat it as such. It's almost basically like the internet, so you'd obviously have some security there and decide how you're going to NAT your internal traffic and all of that on your end. But now VPC1 could talk to public resources anywhere in all of the US regions over that public interface. It would just have to come down and go out your routing infrastructure. And similarly, all your internal networks now, whether they're accessing S3 in Oregon, like we described, or whether they're even actually surfing Amazon.com, that's also in the public domain. So it's going to go across this dedicated fiber link. So real quick, as I know we're close on time, see what your VGW sees. So when you start doing this, you start creating mini Direct Connect interfaces, and you're dealing with a lot of BGP announcements. It sometimes gets confusing on what actually each VPC is seeing. So the tip I always recommend is create a hollow route table, if you will, something you're not actually going to assign to any subnets. Keep it off to the side, tag it as your routing database, and enable what we call route propagation. And you do this on the actual route table itself, and as soon as you enable it, the route table is automatically populated with whatever BGP announcements are hitting the opposite side of that VGW. So all of a sudden, now you see everything that VPC sees. So you can see your internal networks, the networks of your other VPCs in the region. So it's a good way just to keep track of what your routing table is. I'm actually going to skip this one real quick. Some more details on Direct Connect. Go straight to going global. So things start to get real fun if you have a network that spans other regions, because now you can start bringing Direct Connect in and connecting it to your corporate cloud. If that cloud also exists internationally, now AWS regions just start to become spokes on your global corporate cloud. And now if you have resources in the US, in Europe, all these VPCs can now start talking to each other over your corporate network. And things start looking like this. So now anyone on your internal network can reach any AWS region over a private Direct Connect connection. And all your VPCs can talk to each other, and you reach all the public resources in different regions. So your global VPC domination is complete. Thanks all. I appreciate your time. I know that was a lot to just throw out there. Thanks for your patience. I'll stay down here